Hello, everyone. So this is our lecture video for section 1.4 functions, which I still believe will be mostly a review or a refresher or bring back to life content area, if you will. Something you should have seen before in previous coursework. And as I've mentioned a couple times, maybe you just forgot some of the lingo, some of how to do that. But once you see it, you should be good with it. I'm going to kind of deviate from my original plan, which was to kind of make 20-minute videos, and I'm just going to run this through. I'm not sure I'm going to stick with my original plan or kind of how I've done these most recent videos moving forward. I thought making 20-minute videos would be best, but instead I might just give you opportunities to make your best judgments yourself, because some of you have already said, I don't mind just one video, and if I need a break, I can pause it myself. And you found it a little tedious to actually jump between the videos. So I'm still open to feedback, what works best for you, and I'll probably send out a survey in another week or two. But I can tell you right now, my intention is this video, I'm just going to go straight through. But if at any point you need to take a break, I would say in between examples is a good time to pause, mark off where you left. Obviously, you would do that in your notebook and then pick back up. So I think that's just a better approach. That kind of fits everyone's needs. If you just want to keep going, then you can. If you need a break, then you can do that along the way. So welcome to section 1.4 functions. And just want to remind us that a function, the definition of a function is a pairing that assigns an input to an output. And we call the entire set of inputs the domain and the entire set of outputs the range. And I don't know if you had the same experience I had when I was in high school or I first saw this, but a common way to first expose students to the concept of a function is really in terms of a machine, like an input-output machine. So you could imagine, let's say, and I'm going to be silly here for a quick second, superheroes. Let me put this over here. So I'm going to say in this can, if you will, it's almost like something we're the almighty power. We can see into this can, and when we look, we see all these different superheroes. So really, I should say nurses, doctors, grocery, stock shelf people who have worked through this pandemic, true superheroes. So I'm actually going to say fictional superheroes, fictional, make-believe superheroes. So imagine all the make-believe, cartoon, not real superheroes were in this quote-unquote can, or this island, as I've used before. So this is what we're going to choose. And then they're going to go through this machine, and that's really like the function part, okay? So the function part is like the machine part, or we say the rule part, if you will. So there's going to be a rule. And I'm going to say this function sorts the superhero into, like, the output is going to say, hey, that's a Marvel superhero. Hey, that's a DC superhero. Or, hey, that's some other superhero, right? Some other type of brand. Okay. So I'm going to stick to what I know, too. I'm not an expert in this. So if I mess this up, please do not scold me too hard. But definitely send me an email and be like, yo, Catwoman is DC, not Marvel, which I think I'm right. So I'm going to stick to the ones I know. That's actually one I was thinking about before the video. So for instance, boom, it's kind of like this, right? So in this can we have superheroes. So I'm going to reach into this and what do I pull out? Wolverine. Wolverine. Oh my God, I can't even spell it. Wolverine. And so it's going to go into this machine, into the function, and what comes out? Marvel. Right. So it is impossible for this to spit out anything else besides Marvel. Wolverine is a Marvel superhero, not DC, not I'm really failing here. I don't know any other comics, but maybe not Disney, etc. Okay, Wolverine is a Marvel superhero. And I'm probably going to get scolded for that because now I think Disney owns Marvel. Whatever. Oh my God, maybe this was a bad example to do. Just hear me out, okay? Play with it. What I'm trying to say is Wolverine has to get one label, and it's Marvel. Whereas something like, I just thought of her name, Harley Quinn. I was thinking, who else? And I was like, oh, that scary ride at Six Flags, the Harley Quinn ride, right? So Harley Quinn, boom, gets pulled out of this can. That's like, imagine, right? She goes into this machine, and the machine applies this rule, and it's like, boom, you are DC. You're a DC. Actually, you're not even a superhero, though, right? Well, some people might think she's a hero. Maybe supervillain. Whatever. I'm doing terrible at explaining this right now. Hopefully you understand the idea, though. The idea is, we take something from here. In this case, I was saying superheroes. Maybe I should just say like fictional characters. Fictional characters. And the rule is it's gonna sort them, almost like the Harry Potter wizard, the sorting hat, right? It's gonna say Marvel, DC, other, right? And so Wolverine pairs with Marvel. That's it. Harley Quinn pairs with DC, not Marvel. Only one, right? Every input pairs with exactly one output. And that's the idea of a function. Let's do something a little more mathematical that I definitely can't mix up. Let's say I have a domain and I don't have all numbers. I just have the numbers 1 and 2 and 3, keeping this really simple. So my domain, I would say, is the set 1, 2, and 3. That's it. It's only 3 things. We call it a discrete set. Discrete meaning it's countable. It's like independent, discrete. Boom, 1, 2, 3. It's not continuous. And the rule will be add 1, then double. So what comes out, all right, well, let's just go through. So what could I possibly pull out? I could pull out a 1. It goes into the machine. So 1 would come in. It gets increased by 1, becomes a 2, and then double. So outputs a 4. Boom. If we played the game with 2, adding 1 to 2 makes it a 3. Doubling that is a 6. And lastly, adding 1 to 3 is 4. Doubling that is 8. So boom. Our range would be 4, 6, and 8. Okay. And notice that 1 pairs exactly with 4 and nothing else. It is impossible to add 1 and double and get anything else but 4. The same can be said for when you take 2 and you add 1 and double, you're going to get 6, and that's it. It doesn't pair with anything else. And lastly, if you took 3 and added 1 double to get 8. So every input here, every pairing, every element in the domain pairs with exactly one object in the range. And if I go back now, maybe to like, let's say Wolverine, Marvel. I also said Harley Quinn, which I'm just going to abbreviate HQ. That was DC. Let's do another Marvel one, Hulk. Excuse me. Why I wanted to go back to this example was to show you the following. Wolverine pairs with Marvel. And that's it. I grab Wolverine. When Wolverine goes into the machine, Marvel is its output. There's no other label associated with Wolverine in this particular rule, okay? Now, Harley Quinn, DC, wonderful, but that's not why I'm stressing here. Now, when Hulk gets input, the rule, it sorts it, and it says, hey, Hulk, you're a Marvel character. Boom, Marvel is the output when Hulk goes into this machine. That's it. Great. So what I'm stressing here is we can have the same output. There's nothing that breaks the definition here. Right? However, where this can get a little bit funky, let's actually break the definition of a function, and then we'll move on. Suppose I had a rule that said, gosh, I should have one much quicker than this. I'm just brain farting right now. Let's just say, oh my gosh, I'm doing horrible. We'll say the domain is a fruit, and what the output is its color. Okay. Now this is going to fail to be a function, and I just should have had this better planned. But for instance, suppose I take apple. Apple is a fruit. Apple comes into the machine, boop, 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 and this is going to, apply the rule, which is to figure out its color. Well, what can apples be? Apples can be red, but apples can also be green. Arguably, they could be yellow. I'm sure there's other colors too, but I'm going to stop right here. Apple can pair with different outputs. That is not what we consider a function, okay? So that's different than Wolverine pairing with Marvel. So one input, you get one output. It's kind of like a soda machine. You make a choice, you get one soda. That's a functioning machine. But if you put in an input like Apple and you get you get a red and a green soda out, I'm jumping across here, but if you get two different outputs, you're happy. Don't get me wrong. You're like wicked excited. You're like, yes, winning. But the machine's not functioning, right? You can't get two different outputs. So it's all about the outputs. As long as you get one output for every input, you have a function. All right, rant over on that. So that's what a function is in general, okay? Big ideas here. Everything that's in that first set is called your domain. So everything that would be right here, and they could be numbers, they could be superheroes or non-fictional characters or whatever. There's some rule that is applied to your inputs, and then this is output set is called your range. And that's the idea about what a function is. A common question, at least at the pre-cal level, will be to ask you to identify which equations represent y as a function of x, which just means for every x, do you get one and only one y value as your output. So the reason I took the time to draw that function machine is, one, to maybe activate some prior knowledge because that's what you've seen before. Number two, it kind of guides the concept for what we're about to do here. We want to kind of focus on outputs. And so when you read how to do this in the book, it's going to say start by solving for y. So basically we want to isolate y because we want to say, hey, here's a recipe for outputs, and then we'll dissect it from there. Okay, so step one is to isolate y if it's not already. So for letter A, I'm going to factor out the common factor of y and get a 2 plus x equals 6. And then I'll divide by that group and say y is equal to 6 divided by 2 plus x. And now these can be quite, challenging if you don't have great number sense or you're not quite sure what to do. But my advice to you is just this. Try a couple like basic numbers. When you see a question written like this in a pre-cal course, the strategy is that the student is just trying a couple of easy numbers to get an idea about what's going on. I know that's kind of vague, so let me just work through all of these, okay? But after you isolate y, now you just want to test a few numbers for x, and then think about, could I possibly get more than one y value? So for instance, I'm going to think in my mind, suppose x was -1. So if x was -1, this would become 6 over 1, and y would be 6. There's no other value it could be. So if I choose -1 as my input, I'm going to output a 6. End of story. So I could say -1 pairs with 6. Okay. What about if I chose 0? If x was 0, this would become 6 over 2. That's 3. 0 would pair with 3 and nothing possible else. So far I have evidence that when I give it one input, I'm only getting one output out. And I'm probably just going to claim that this is a function. I will do one more example just to kind of confirm it to myself. Maybe I'll choose something like 2. If x is 2, then I get 6 over 4, which is 3/2, which is 1.5 as a decimal or mixed fraction. But I'm still only getting one output. So I have evidence to say for every one input, I'm getting one output. Yes, y is a function of x. That's it. It's a little bit of just number sense and just plugging in and see if you possibly get more than one values as an output. Let's go on to letter B. So to solve for y, to isolate y, I'm actually going to not isolate y. I'm just going to isolate the absolute value of y and call this 6 minus x. Okay. And now again, I'll choose some numbers. So for instance, maybe I'll choose 0 and then figure out what it pairs with. So if x is 0, I'd be thinking the absolute value of y has to make 6. So what could y be? And here's where you need to like have your number sense and like not just rush things. And especially when you answer a question like this, just saying, you almost want to say, can I possibly get 2 answers? So when I'm looking at the absolute value, that's one I'm familiar with from my work to say, hey, I know that there's 2 y values that would work here. Right? So if this was the number 6, that would be true. So I'm going to write 6. But what would also be true is if this was -6. So I claim we have the following 2 pairings that satisfy this equation. So I'm going to go erase all this and double check it. If x is 0 and I substitute in 6, take its absolute value, that does make 6. Substitute in 0, take the absolute value of -6, that also makes 6. So yes, these are indeed solutions to that equation, but I can answer the question posed to me as no. Wait, what? I'll say that again. Yes, these are solutions to the equation, but the question is y a function of x? 0 is pairing with 6. 0 is pairing with -6. That's an issue. Again, think of this as Wolverine saying, hey, Wolverine, I'm Marvel. Boom, I'm Wolverine. I'm also DC. I'm 2 different things. No, that's not possible. That's not functioning. All right, that's what a function is. Letter C, for time's sake, I'm going to tell you right now the answer is yes, and you can check that yourself. All right, I'm just noticing the time is moving faster than I want it to, but main point I put that on there for is there are other examples beyond the absolute value, and don't just conclude to yourself that, oh, I see absolute value, it is a function or it's not a function. You have to be careful. All right, so my focus to you, my word of advice to this course, to you in this course, is think, reason, justify. Don't just try to game and trick the system or trick me. All right, learn the content. So anyhow, end of rant. I want to stick to the focus here. Moving on. So we're 20 minutes in. I guess if you do need a break, be a good time, but we still have quite a bit to do in this lecture. So if you can hang in there for a bit, hang in there. So we're just breaking the ice, to be honest. We're barely, I don't even think we're 25% through with what we need to. Okay. What you are probably also or should be familiar with is function notation. So if you need some additional reading, obviously refer to the textbook or do your own web sleuthing on it. But function notation is just a way that we convert equations that represent functions into some fancy form, right? And basically what you need to be able to do is not just know what function notation is, but to evaluate functions in function notation. So here is a function, f of x is 5x minus x squared. And the word I really want to focus in on is evaluate. So to evaluate a function, you go to, if I were to kind of make a machine for this, it would be something like this. X is coming in, and then what? We're going to multiply 5 times it, and then minus x squared. So this is the actual function part, and what comes out. So that's the rule. That's what we actually do. And that's what's going to come out. What comes out is what we say f of x, or whatever that number is. Okay, so that's the idea. Again, I didn't do, I'm assuming, and I have to assume, this is not your first exposure to functions. This is not how I would teach it if we were in college algebra or in an Algebra 1 type course. It's a refresher, okay? If you need additional explanation, then that would be a great time to reach out to me and let's talk about it in office hours. And if you want additional examples, we can do that in office hours. Whatever you want office hours to be, I'm happy to do extra examples or just extra explanations or state it another way so that you make sense of it. But anyways, that's what's kind of going on here, right? So in this case, it's saying, all right, now I'm going to take, well, look what happened. X now is becoming -1. So it's like I'm taking -1 and it's going into this machine and it's saying, do this rule to it. And what's going to come out is f of -1. But we're going to actually find the rule. We're going to state exactly what that is. Meaning we're going to take -1 and replace it everywhere we see x. Okay. That's what's going on here. So I'm going to do, that's my last function example for now. Everywhere we see an x, we're going to replace it with a -1. Now, when I set these up, I kind of just write what I see. And anytime I see an x, I open up a set of parentheses. So just bear with me if you're wondering what I'm doing. So when I look at this rule, I see 5 times an x, which means I'm going to open a parentheses, and then a minus, an x. So I'm going to open a set of parentheses, squared. Okay, so what I'm doing is everywhere that's an x, I'm opening a set of parentheses. Otherwise, I'm just copying what's written. Now I'm going to substitute in the -1 into each of those groups, into each of those parentheses. And now just follow the order of operations. This becomes -5. -1 squared is 1. So -1 more. Our final answer is -6. F of -1 is -6. Okay. All this means is that -1 pairs with -6. F of 3y. Again, I'm going to write what I see. Anytime I see an x, I open a set of parentheses. 5 minus, okay. Now we're going to substitute in 3y into each of those groups. So just like before, that's a parenthesis now, and that's a parenthesis. That's what's getting replaced with 3y. And now just do the algebra. The algebra says to, well, in this first term, we're looking at 5 times 3 times y, which is 15y. And in this second term, we have 3y times 3y, that's 9y squared. And we're done. F of 3y is 15y minus 9y squared. You could factor it, but I'm not asked to. That's not the intention of this lesson. Just if you recognize you could factor it, great. If you did, no one would mark you wrong. But right now, that's not the intention of this. This is just taking and evaluating a function for numbers. And so far, we've done it for an algebraic expression. We're about to do it for another algebraic expression. And just notice when you take an algebraic expression as your input, most likely you're going to get an algebraic expression as your output. And when we've had a number as our input, we got a number as our output. So just to reemphasize that, letter A, we had a number as our input. We're getting a number as our final output. In letter B, we had 3y as an input. So we have this final expression with variables as our output. Okay, do this one more time. So we have 5 times x, but I'm going to open a parentheses, minus parentheses squared. And so now I'm replacing every parentheses with an x plus 3. Okay. If you set it up like I'm setting it up, there is no way you can ever get these wrong. Okay. Moving on. So we can distribute the 5 and call this 5x plus 15. Talked about this in the last video. Do not distribute that negative sign until you do your exponent. And you should be practicing expanding these really quick. And now distributing the minus sign and combining like terms, we would end up with a negative x squared minus x plus 6. That would be our final answer. F of x plus 3 is equal to negative x squared minus x plus 6. Great. Letter D, a couple more here. Sorry. Find f of x plus 3. So what this says is to just write the actual function, replace what f of x is with its function rule, and then add 3 to it. So f of x is, well, if I'm confusing here, let's just do what I said. We're going to write the rule. And then this says to add 3 to that. So this is what I'm kind of stress here, the notation, all right? And then everywhere we see a group, we put in an x. So notice what we're getting back is exactly the same thing, except a plus 3 here. And we're done. There's no like terms. Maybe I'll just rewrite the order in standard form. But we are done. Okay. In addition to just paying attention notation, I wanted to stress, if we compare parts C and D, it shows that f of 2 terms is not equal to f of the first term plus f of the second term, all right? I'm not even sure our book says this, but sometimes basically what I'm trying to say here is students think, and you should not, this is like a major fundamental, do not do this in your thinking. Functions do not distribute into those expressions. That f is not a number. It is a name, okay? The distributive property says distribute numbers in front of groups. That's the distributive property. But f of 2, f is not a variable. F is not an unknown number that could be distributed. F is just the name. It does not make any mathematical sense to distribute f. I don't even like saying it because it doesn't make sense. In addition, even if you thought you could, right, what I'm arguing here is if I clean this all up, some students incorrectly, they bogusly think, oh, f of x plus 3, well, that's f of x plus f of 3. Actually, that's probably what I should have showed in that video, but this is actually false too, right? This is not true. Do not distribute the f. Wrong, 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 wrong. And if you do that, no matter what you write after it, you are going to be marked 100% wrong on that question. 0 partial credit at any point in this course, and I can guarantee you beyond this course, right? If you were a calculus student and did that, I would really question if you were ready for calculus. Do not do that. It will earn you nothing, even if everything else is amazing after that. Okay. Last part here. Find all real values of x such that f of x is 4. And this, after this little part, might be a nice time for a little break. So this is not asking us to take an input 4 and then find the output. I am going to just show a function diagram of what this means. All right. So this is saying, hey, find all x. So find all the x values that when they go through this rule, give out 4. So we need to figure out what inputs go through this function machine into this rule right here, and then eventually output 4. That's what this is asking us to find. Okay, so I'm going to clean this all up and actually do it in a nice, coherent way. Well, this is pretty simple. We're going to replace f of x with its expression, which was 5x minus x squared. And then we just carried down the equals 4. And now solve this equation. I'm going to add x squared to both sides. I'm going to subtract 5x on both sides. And then I can factor this as x minus 4 and x minus 1, which means x could be either 4 or 1 by the zero product property. And I can check that pretty darn quickly. Check. F of 4 does indeed make 4, and f of 1 does indeed make 4. What I just did in my head, or I did before, but I'll talk you through it, put in 4 right here, right? So f of 4, this is 20 minus 4 squared is 16. That gives you 4. Boom. So when we input 4, the output is 4. And when we input 1, this becomes 5 times 1, which is 5, minus 1 squared is 1, 4. 1 also outputs 4. And we did it. We answered the question. Find all the inputs such that the output is 4. The answer, I boxed it below there, is 4 and 1. Right. So we're a little more than 30 minutes in, about to switch gear into something called piecewise functions and move beyond into more concepts from here. But if you want to take a quick just refresher and come back, do so. All right, we are now moving onwards. A function defined by two or more equations over a specific domain is called a piecewise defined function. And what I did, this is not in our book, but I like to actually use this example as an introduction, as I'm doing with you, and potentially on your first quiz or midterm or even final, is write a piecewise function. Like, here's how they kind of have some real life meaning in a very easy sense, but you can start to appreciate it and then build up from here. Joe earns an hourly rate of $16 an hour for each hour worked up to and including 40 hours. So he earns basically $16 an hour for the first 40 hours. Joe is protected by laws in the United States, right? So when you work for an hourly rate, you up to 40 hours, you get that rate. Up to and including 40, you get paid that rate. Now, after 40, most of us know, you get overtime or time and a half or 1.5 times your rate. Minimally, some people are lucky enough to get double time and et cetera, but I'm not going to rant too much today. Any number of hours worked beyond that 40 is paid at what is called time and a half, and I just explained that as 1.5 times your pay. So write a function that gives the amount of money M Joe earns if he works H hours. Then use your function to evaluate M of 20 and M of 50. What are the units for the 20, M of 20, the 50, and the M of 50? Quite a mouthful there, but we can do it. All right, so we're going to write a function M that gives money. Well, I'm going to start with words first. So the amount of money he works is as follows. It is the money earned, money for H hours is equal to, well, we kind of have a couple cases. So the first case is it's $16 per hour. $16 per hour. If you're cool, I'm just going to call this 16H, where the number of hours is less, greater than or equal to 0, less than or equal to 40. Okay. Now, after 40, he's going to get 1.5 times that hourly rate. So if you take 16 and multiply it by 1.5, that ends up becoming 24. So basically, after 40 hours, he's making $24 an hour. Now, this is so far, listen, this is incorrect right now, so far. But I'm going to show you what most students kind of write here. So they say for H greater than 40. So I'm going to pause for a minute. I'm going to fix it. But do you know why this is wrong? So for instance, if he works 41 hours, should I just do 24 times 41? Does that mean if Joe works 41 hours, so by the way, I'm writing something bogus here. Is it true that he'll make $24 for all 41 hours? That would be nice, but the answer is sadly no. Okay, he's not getting paid $24 an hour for all 41 hours. He's only going to get $24 an hour for 1 hour, right? What if he worked 46 hours, let's say? Would he get $24 for all 46 hours? No, we have to do what? He would get $24 an hour for 6 hours. So what are we doing? We are subtracting 40 to figure out the overtime hours, okay? So this right here is not 24H, but it's $24 for each overtime hour. And how do you find an overtime hour? You need to call this 40, H minus 40. And now I think we're in business. Are we? No, we're not. We still have to add on what? We still have to add on 16 times 40. And I'll explain why here. Out of room. So I'm going to rewrite all this nice and clean. Okay? Kind of walk through it. Let's do this nice and clean. I'm going to do this in functional notation. The amount of money he works for H hours is definitely 16 an hour for any amount of hours between 0 and 40. No one has an issue with that. Now what we need to figure out is his overtime pay. So he's going to earn $24 for each overtime hour. So that's H minus 40. But we still have to pay him for the 40 hours that he's worked, right? So we still have to pay him his 40 hours at $16 an hour. So 40 times 16, which I guess I could just use my calculator right here. 40 times 16, that's 640. for any hours greater than 40. Okay. Let's just confirm that this kind of makes sense, right? To me, it does. I'm hoping to you it does too. So let's think about this with the following. Let's find M of 20. So M of 20, he's worked 20 hours. So it just makes common sense that we should multiply 16 times 20, which that's what this says. Since our H value is in between 0 and 40, use this rule. Use this equation part. I lost my 0 there. Okay, so we're going to do 16 times 20, known as 600 and, no it's not, times 20. 16 times 20 is 320. Didn't even need a calculator for that, but I still used it. Okay, so if he works 20 hours, he'll make $320 before taxes. We all know that stinks too. What about M of 50? Okay, so the amount of money he'll make for working 50 hours is $24 for each hour over 40. So we need to subtract the 40. So I'm just using this rule here. But we still have to pay him the $640 for the 40 hours that he's worked. So he's going to get $24 for 10 hours plus his $640 for the 40 hours, for a total of $240 plus $640 is $880. Boom. Just want to box these two numbers here. And I hope that makes sense now. So if you've never seen a piecewise function, there's how you can use one to model like pay scales, if you will. Okay. The last part of this question asked us to identify the units for 20, M of 20, 50, and M of 50. So I'm going to kind of kill this two birds with one stone. Both 20 and 50 are inputs. They represent hours. So 20, the units associated with 20 is 20 hours, and the units associated with the 50 is 50 hours. Right? But what we found is the units associated with M of 20 equals dollars. It's the amount of money at 20 hours worked. So M of 20 has a unit of dollars. And the same could be said for M of 50. It represents dollars. M of 50 represents the amount of dollars he will earn for working 50 hours under those or under that criteria. Right? So that's a piecewise function. That's writing a piecewise function. Here's something a little less word problem-esque. That's just asking us to evaluate three values, f of -2, f of -1/2, and f of 3 for this piecewise function. So let's get to it. F of -2. So my x is -2. This says when your input is less than -1, hey, guess what? -2 is less than -1. Then use this recipe, 3 times x minus 1. So this will be 3 times the x minus 1. I input the -2, follow the order of operations, and this makes -7. Done. F of -1/2. F of -1/2 is, oops, I'm lying. So why can't I use the same rule again? Well, -1/2 is not less than -1. It's not, okay? But -1/2 is in this interval between -1 and 1. So this says, hey, use this rule 4. All right, f of -1/2 is 4, and we're done. Boom. Right? That's just what we call a constant rule. It always outputs 4 on that interval. Last but not least, find f of 3. So where is 3? Is 3 less than -1? Obviously not. Is it between -1 and 1? No. Is it greater than 1? Yes. So our input of 3 is greater than 1, which means we use this equation or this case or this part of or this piece. That kind of fits nicely. It's a piecewise function. Use this piece. So we would say it's f of 3 is x squared. Again, I always, at least right now in this video, I'm going to try to use parentheses, get us back in the mindset. But I'm saying x squared, but I'm writing parentheses squared. And now I input the 3, do the order of operations. Really simple, 9. All right, so that's a more classic example of what a piecewise function looks like. Number 5, find all real values of x such that f of x is 0. We've seen a question like this not too long ago. It looked like letter E, right? So we want to find all the x, and I'll do it again in this video. This is basically asking us, hey, find all the x such that it goes through the rule and you output 0. So it's that type of question again. But this is so common that this is called finding the zeros of a function, and that's a vocab word. Okay, this is finding the zeros of the function. I believe, I could be wrong, but it's in my mindset right now. I believe the questions that ask you to find the zeros are not in section 1. What is this, 1.4? This is section 1.4. I wrote this question in 1.4, but I believe it's actually in homework questions 1.5. So just an FYI, just giving you a heads up there, okay? So find all the zeros of this function. You'll probably practice questions like this, I believe, in sections 1.5, but you'll do it in one of them. Maybe I'm just confused. It might have been, maybe I'm thinking of something else. All right, so what we're going to do here is, as we've done before, we write the rule, x cubed minus x, set it equal to 0, and then we solve this, solve by factoring. X squared minus 1 equals 0. We can factor completely as x minus 1, x plus 1. And then by the zero product property, x could be 0, 1, or -1. So we can call that plus and minus 1. And we're done. Those are our solutions. 0, plus and minus 1. You can check that yourself. Letter B, find the zeros. Again, write your function rule. Set it equal to 0. Solve this by cross multiplying, adding x squared to both sides, and then subtracting 5. Why am I subtracting 5? I don't know. So cross multiplying would be 0. Adding x squared to both sides, and then just extracting the roots or taking a square root, you get x is plus and minus the square root of 12, which the really only reason I showed this is I think WebAssign, I'm sorry, would give you credit for this, but we probably want to make sure we simplify our answers as 2 times the square root of 3. So both positive and negative, 2 times the square root of 3. All right, where are we at? Example 6 kind of follows exactly from before. It's saying, hey, find all real values of x such that f of x is equal to g of x. So it's basically saying, it's really easy to set up, but just so you can kind of understand what all these symbols on the paper mean, think of it as we have 2 machines. So we have rule 1, rule f, and then we're going to take the same x and we're going to apply it to rule g. Right. So, and then what you get here is obviously some output. from the F machine. So you get f of x. And then what you get here is some output from the G machine, which we call G of x, okay? And this is saying, hey, what numbers do you put to this rule and this rule such that these end up being the same? So we want the outputs to be the same, right? So that's the idea of this question. It's two different rules, but the same input. What inputs do we run through two different rules but still get the same values? So let's do that. That's the idea of this. Now this is nothing more than just substituting the expression for f of x on the left and then substituting the expression for g of x on the right. So we know that f of x is the square root of x minus 4. We're told that right here. And we're setting that equal to the expression for g of x, which is just 2 minus x. Okay. And we solve this equation by isolating the square root. So last week we solved equations, and some of them were square root equations. So you want to isolate the square root, then square both sides. And when I square that binomial, I get 36 minus 12x plus x squared. And I can subtract the x to say 36 minus 11x plus x squared. And I'm going to switch the order here. X squared minus 11x. Oh, I'm sorry, 13x. When you subtract one over, this should be minus 13x. Subtracting x on both sides. I don't know why I said 11. Arithmetic mistake. Glad I went back and changed the order. And then I'm going to see really quick, can I find factor pairs of 36 that have a sum of negative 13? And I did it really fast as negative 9 and negative 4. And by the zero product property, x is either 9 or 4. So I'll choose one of these just to confirm to you that, oh, and we should always check our answers, right? We should always check our answers when we square both sides of an equation. So check for extraneous. I'm going a little too quick here. Checking is not just you should, but it's mandatory. Because whenever you multiply or divide by a variable or square both sides, you could potentially get extraneous solutions. So let's see. F of 9 and g of 9. F of 9 is the square root of 9, 3. Take away 4 is negative 1. And when we input g of 9, we get 2 minus 9. Uh-oh, that's negative 7. Oops. Nope, that's extraneous. Bing, bing, not true. Let's check 4. F of 4, g of 4. Square root of 4 is 2. 2 remove negative 4 is negative 2. And then 2 minus 4 is negative 2. Boom. That is true. So I shouldn't even box that. The answer is when x is 4. 9 ended up being extraneous. Okay. But what I'm also showing you here, and think in terms of function machines, I'm not going to draw them, but 4 is coming in. It gets hit up with rule F. You output negative 2. Notice we're taking the same input 4. It's going through a completely different rule, but you're getting the same output. And that's what this question asks us to find. Find the inputs such that the outputs are the same for two different rules. If you need another quick break, we are, let's see, let me just peek ahead here. A little bit to go. Might be time for a little break. Still got some more to go through. Maybe halfway right now. So here we are. The domain of a function, we talked about it in the appendix section, but I'm just restating it. It's stated in the section 2. Your call if you want to copy it down again or not. But the domain of a function, I think when we talked about it before, is the domain of an expression, but same idea here. The domain of a function is the set of values such that the function is defined. Meaning, if I'm going back to that superhero or fictional character machine, okay, so way back before, if you take and input a character, it's going to tell you Marvel, DC, or something other, right? And we already went through that at the beginning of this lesson. But right now, suppose you asked it to sort Sour Patch Kids. That's what I'm looking at. Well, Sour Patch Kid is not a, if you don't believe me, it's right here. Sour Patch Kid isn't Marvel, isn't DC, and it's not other because Sour Patch Kid wouldn't even be in the idea of fictional superheroes or supervillains. Sour Patch Kids is a candy. They're make-believe, but they're not any type of hero or supervillain, so they wouldn't even be in the domain. Right? So it's not, we wouldn't even say exclude Sour Patch Kids. They wouldn't even be there from the beginning. All right. Anyways, just a little rant on that about what it means to be defined. Right? So if I say, hey, what's F of Sour Patch Kid? The machine would be like, I can't sort that. That's not a superhero. That doesn't make sense to me. Right? So it wouldn't even be in the domain because it would not be defined. We mentioned polynomial expressions were always defined. Well, guess what? Polynomial functions are defined for all real numbers. And the same can be said about odd root functions. The domain of rational expressions from last week was any number that caused division by 0. Well, for rational functions, same idea. Anytime you have an input that causes division by 0, we need to exclude it. And for square roots or any even roots, again, very similar to last week's expressions, same commentary here. Now that we're talking about just functions, we can say that the domain of a square root function is all real numbers except any causing the radicand to be negative. And that's not just true for square roots, but 4th roots, 6th roots, and beyond. Letter A, f of t is a cube root of t plus 4. A cube root is an odd function by assumed fact. The domain is all real numbers. And in interval notation, we write that as negative infinity to infinity. So we're going to continually work on interval notation. Letter B, we have a square root function. So we want to find all the values, x cubed plus x squared minus 4x minus 4, such that this is greater than or equal to 0. We can factor this expression, taking out the common factor. Factoring out the common factor here. So we get an x plus 1, then an x squared minus 4 greater than or equal to 0. To solve this inequality, remember last week I showed us to solve inequalities, you're basically finding your key values and solving the related equation. So our key values, now that it's in factored form, are 1, -2, and 2. And then we would choose some values on different intervals and see whether or not they are true. So if I choose a number less than -2, like -3, this would be negative and this would be positive. No, that is not greater than 0. Does -2 work? Yes, because we're allowed to be equal to. I don't know why I have 1 here. It should be -1, shouldn't it? Yes. So by the way, all these key values work. How about in between -2 and -1? So a number like -1.5. Well, this would be negative, and this would be -1.5. Let me just check here. I can't do it in my head. 1.5. That was 1.5. This would also be negative, and a negative times a negative is positive, so that's good. So all the numbers in this interval would work. If we choose a number between -1 and 2, like 0, this would be positive, this would be negative, so this would not work. If we choose a number greater than 2, this would be positive, this would be positive, so numbers here work. So our domain is this is very similar to last week. It's almost just an extension, finding the domain of function. You're using factoring strategies, you're using inequalities. We would say that this is -2 to -1. Oops, I need brackets. Union 2 to infinity. And that's my domain for this function. Okay, very similar to last week's. All right, that's why I did it, just to break the ice. And now we're just throwing it in the terms of functions. What's the domain of this? We've seen this before. We have kind of two issues going on here. By the way, this is not a rational function. A rational is a polynomial over polynomial. This is a polynomial. This is not. Okay, so this is not considered a rational function, but it is considered a quotient function. Anyhow, we have two things. X minus 1 has to be greater than or equal to 0. The radicand has to be non-negative. And x minus 4 cannot be 0. All right. So we have those two situations. Oh, I meant to put the word and. I said and, but I wrote the word union. All right. So solving this inequality, x has to be greater than or equal to 1, and x cannot be 4. So from last week, from that discussion, and statements must both be true. So these numbers that satisfy this are equal to 1 or greater. The numbers that satisfy this is everything except 4, but the numbers that satisfy this and that have 1 to 4. You can be 1, but not 4, joined with 4 to infinity. And that's the domain for this function. All right, switching gears. One of the most basic but introductory definitions in calculus is called the difference quotient. And the difference quotient is the following expression: f evaluated at x plus h minus f of x, all divided by h. And there's always an assumption here, h can't be 0 because we never want to divide by 0. But I'll leave it at that. There's a lot more to this story in calculus, but you will absolutely work with this expression repetitively in Calc 1, right? You need to be able to work with this expression in Calc 1. And when I say work with it, it's what we're going to do right now. You're going to extend what we're going to do in this course in calculus. So for us, know this formula for the difference quotient. I will not give you the difference quotient on any exams. You do need to memorize this. Now, I know I'm not going to lie, and I'm going to call it right out. You're probably going to have a little cheat sheet to the side. So I know that in the back of my mind when I'm writing the exams this fall semester. I'm writing them with the intention that you're going to break the rules, although I hope you don't. But anyways, I'll leave it at that. You, as a good student, you want to be prepared, you want to be better than the rest, if you will, you're going to study that and be ready for the exam. And that's that. It's like I tell my Algebra 2 students, they want to be ready to memorize the quadratic formula. And the quadratic formula is way worse than that thing. Let's find the difference quotient and then simplify your answer enough so that substituting in h with 0 would be allowed. All right. So this is almost like, this should say far enough so that substituting h with 0 should be allowed. So we're not allowed to substitute in 0, but you know your answer is completely simplified when you could pretend to substitute in h with 0 and there wouldn't be an issue, right? So that's what I tell calculus students. That's when you know you're done simplifying. Okay, so first we write the difference quotients. f of x plus h minus f of x. So my roommate's coming home, by the way, and the dogs are going to bark in a second.
Hello.
Hey, what's up?
Did you see the pads?
Yeah, I'm in class right now, though, but yeah, I did. Thanks. No problem. So f of x plus h. We're going to replace every x with x plus h. All right, so let's get started here. So everything, I'll do this in blue. All right, so looking here, everywhere I see an x, I'm opening a parentheses. And I'm going to replace it with what? X plus h. All right, that takes care of this first piece. Minus f of x. Okay, so do this part in red. So we're going to do minus. Okay, there's multiple terms, so I definitely need brackets here. And then this cube plus 3 times that. We're just going to replace this with x. And then divide that all by h. Whew. Okay. Well, there you go. So take a breather there. Look at it. Check it. Hopefully that makes sense to you. All right. I could definitely put brackets around this as well. And some students just like that for completeness. But notice they're not necessary for that first highlighted blue part, but it's absolutely necessary for this part written in red because it has multiple terms. And when we go to just subtract, it's called a difference quotient. Anytime we have subtraction, we must proceed with extra caution. And now it says to simplify to a point where you should be able to substitute in h with 0. Well, guess what? Until we get h out of the denominator, we have a problem. So the strategy, at least with polynomial expressions, is to always expand polynomials, combine like terms, factor, and things should be designed to cancel out for you. All right. So expanding, we get x cubed plus 3x squared h plus 3x squared plus h cubed. Distributing the 3, we get 3x plus 3h. And then we'd have a minus an x cubed, and we'd have a minus 3x, all divided by h. And off we go. X cubed and negative x cubed cancel. 3x and negative 3x cancel. And if you look at this term, this term, this term, this term, they all have an h as a factor. So in my next step, I'm going to factor out the h. And this becomes 3x squared plus 3x h plus h squared plus 3h. Yep. No, plus 3. All divided by h. And now we can cancel those out. And I'm on a tablet, so I'm lucky enough to do this. Boom. That's our final answer. So it's a bunch of algebra. It's a bunch of evaluating functions and working carefully. So with polynomial expressions, as I said at the beginning of this, you should always expand, combine like terms, and then factor. And if you've done your work right, you should be able to cancel that h, unless you get to Calc 2, and that's why it's called Calc 2. So when that process fails, you need something else. But in Calc 1, most of them are designed that way. Or they might be designed with square roots. So let's see what happens here. Again, I'll write the difference quotient, f of x plus h minus f of x, all divided by h. And, okay, grab my little highlighter here. So the first part here, we start writing everywhere we see an x, we replace it with parentheses. And then we're putting in what? X plus h. Wonderful. Minus f of x. So we have the square root of everywhere see an x, parentheses. And if you put a bracket here, that's fine. Although, and I get it, it's really not two terms because it's those two terms are underneath the grouping symbol, so they're not necessarily needed here. And all of this needs to be divided by h, right? So we're at this point, and what can I simplify? Well, actually, it doesn't look much to simplify. I can ditch those parentheses and call this x plus h minus 1. And the same argument over here, this can just be called x minus 1. And the other strategy is, first of all, we at a point where I can substitute in h with 0. Even though I'm not technically supposed to at all, it's like that's how you know you're completely simplified. No, I still can't because I have division by 0. So somehow I need to get h out. And these are not polynomial expressions. I can't expand and combine like terms and factor. But last week we did review rationalizing the numerator. Okay, so let's try rationalizing and see where that leads. X plus h minus 1. And then we change the sign. So rationalizing means you multiply by a conjugate pair. And we know that in the numerator, we have a pair of conjugates, and when we multiply those, they form a difference of squares. So we get x plus h minus 1 minus x minus 1, all divided by h times the square root of x plus h minus 1 plus the square root of x minus 1. So we're just going to leave that factor down there. Distributing the negative sign would make a 0 pair with that and with this term. So those cancel out. So I'd have the h on top of h times the square root of x plus h minus 1 plus the square root of x minus 1. And then we could cancel out our h's. And again, I'm on a tablet, so I get the benefit of not having to rewrite it again, just deleting it, and there's your final answer. Because now, when I substitute in 0, I don't have a division by 0 anymore, right? I'm not dividing by 0. I'll be in business. Right. So you basically want to continue to simplify until you can cancel out that h in the denominator. I'm going to pause this video at this. No, let me finish up this one because it goes along nicely here, and I'll save those for a future lesson. So this will be my last video example here. These were extension questions anyways, but I'll put them on the review sheet later. They're not on your homework for right now. Example 9, simplify this expression. So I'm not calling it the difference quotient, but it definitely has the structure of the difference quotient, okay? Has the structure of it. But the difference quotient is that formula. You have to evaluate it at x plus h, and so on and so on. We're not quite doing that here, but it has the same kind of structure, right? Meaning we're going to find f of t, subtract f of 1, and then divide it by t minus 1, where the function is 1 divided by t minus 2. All right, let's do it. So f of t is 1, oops, that's highlighter. 1 divided by parentheses minus 2. And we're inputting t, so this just becomes t minus f of 1. Well, that's easy. When I input 1 here, 1 divided by 1 minus 2, that's negative 1. And then this says, so if you see where I'm going with this, we're not actually evaluating anything here. This just says, hey, this just says, don't evaluate the function, just put it over t minus 1, all right? So pay attention to notation, okay? This says f of t, so we need to evaluate f at t. This says evaluate f at 1, but this is not f of anything. This is just the expression t minus 1. There's no need to evaluate here. This just says write t minus 1. Okay. And let's clean this up. We get 1 divided by t minus 2 plus 1 over t minus 1. And again, from last week, kind of all the ideas, the skills that came in last week, we can deal with this complex fraction by multiplying by the least common denominator. In this case, it's t minus 2 to both the top and the denominator. And when we distribute, we'd get a 1 plus a, since plus, I don't need any parentheses here. And then to divide this by t minus 1, t minus 2. Try to keep things factored because a lot of things are designed to cancel. And when they're factored, we can see that they cancel. And in the numerator, I can see that 1 and negative 2 combine to negative 1. And so this ultimately becomes t minus 1 over t minus 1 times the factor of t minus 2. Cross those out, and our final answer is 1 divided by the quantity t minus 2. So thank you for hanging in there. And the passcode for week 2, the first passcode for week 2 is sour, in honor of the Sour Patch Kids from earlier today. So I'll see you in the next video. Thank you for hanging in there.